So I'm going to continue talking about this, about phase changes. And when we look at a solid like I drew yesterday, solid right here, all right, um, it would have, in order for it to be a solid, it's considered to have high attractive forces. And attractive forces are those forces that hold molecules or ions or atoms together. They aren't bonds, they aren't covalent or ionic. They're actually called van der Waals forces by some people, but they're intermolecular forces, so they're holding each individual particle to each other. So solids have a high level of attractive forces. Liquids have low attractive forces. And by definition, a gas has zero or no attractive forces. And so once you have no attractive force, you're able to act independently and move around and change. And it is these attractive forces that you're manipulating with temperature and pressure. So now I want to talk about where evaporation comes from. And if the key to understanding evaporation is, I want to start off with a graph. And on this graph, I'm going to label temperature down here. And we're talking about temperature that is proportional to average kinetic energy. Kinetic energy is the energy of motion. And I'm going to graph that against, over here, number of molecules. Anyway, if I were to look at this graph and say I'm looking at the room, and I measured all the kinetic energy of all the gas particles in there, I would find that I would get a graph that would look something like that, with the average being right here, room temperature. And let's say room temperature today is 25 degrees Celsius. Okay? So that means that there are going to be some molecules that are moving faster than the average. Over here, it also means that they're going to be moving slow, some moving slower, but on average, they're all going to be about 25 degrees Celsius. Well, with liquids, since there is this random motion, since collisions are elastic and they can be bumped together, and every now and then a few molecules might just happen to get enough kinetic energy to overcome the attractive forces that are holding them in a liquid and turn them into gas. Because that's what you're doing when you're getting a substance to, boil, is you're making the attractive forces, overcoming them with this molecular motion. So this little portion right here of those that I just drew would have enough kinetic energy, because they're the fastest moving, that can break the attractive forces holding them as a liquid, and they are going to go away and evaporate. Well, the result of this graph is, now I get a lowering effect of the average. The average would be somewhat lower, and this is exactly why sweat is, because sweat is a cooling property, because it lowers the temperature of whatever is, next to that which is evaporating. So after a while, the average would then reestablish itself back to where it was, but then those would go again, shifting it back, and this whole process would go until that substance evaporated away. So that's how we describe evaporation. Better spell it right. And it is a result of the fact that some of the fastest moving molecules in this collection of a whole bunch of them, have enough kinetic energy to overcome the attractive forces that are holding them as a liquid, thereby turning them into a gas. All right? So keep that in mind with evaporation. Now what I'm going to do is I'm going to talk about something called vapor pressure. And I'll talk about vapor pressure in class too, because it's kind of complicated. But um, what happens is, if I go back and let's say I have this flask sitting on the table. It looks like this. Oops. The greatest flask. It looks like that. And I have a little bit of liquid in the bottom of it. Well, that liquid is going to start to evaporate. All liquids evaporate. All solids evaporate to some extent. You buy a new car, you have that nice new car smell. Well, that's coming from evaporating plastics making up your dashboard. Everything will evaporate to a certain point. So, as this liquid starts to evaporate, I am creating gas particles. Normally those gas particles that evaporate just go back out and soon disappear up wherever they're going. The amount of liquid in the flask gets smaller and smaller and it evaporates away. But let's say I came along and I put a cork on that flask and I just sealed it up. Well, if I seal that up, I've trapped these blue gas particles in there. So I have all these blue gas particles that are trapped inside. Well, they're going to do what gas particles do. They're going to start colliding with the side of the container, exerting a pressure. So they're going to be smacking themselves against the side of this closed container, and that is going to be a pressure, and that is what vapor pressure is. So vapor pressure is the result of evaporation in a closed container. All right? So we're going to build on this whole evaporation stuff too, and vapor pressure. But basically, if a substance evaporates quickly, it will also exert a high vapor pressure. If something doesn't exert a high vapor pressure, it's going to be a substance that evaporates very slowly. And it's all due to the fact that you have an average collection of molecules in any given substance, and sometimes there are a few fast ones that are going to be able to escape the intermolecular forces holding them together, and they're going to go into a new phase.